Okay, so here we have our Emacs window um, with an R shell. We load our model, load slicesampler.r, and run slicesampler demo f. F is a function that is proportional to the density. So it's basically an unnormalized density. Here we go. So we start out with this point, which fortunately is closer to the center of distribution. It's pretty close. Okay, so we missed a couple of iterations, so I'll explain the next one. Okay, so we got this x. It's going to turn black because it was accepted. And then we're going to draw a vertical line through this point between 0 and the value of the function. And now we're going to sample uniformly over the length of this line, which we will draw as a horizontal line. Wow, that was at the very extreme outcome. Okay, so, and now we create a big enough interval to cover this area, and we sample uniformly. The first sample over here on the right was rejected because it's above the curve. The second one was accepted because it's below the curve. And now we're going to draw a vertical line through this, which is pretty much at the peak of the distribution. And now we got this horizontal line down here. And we find an interval big enough. And now we sample uniformly, and we get this red X, a vertical line through that. And wow, we're getting some pretty high up points. Most of the time the samples are down here at the thicker part of the bell curve. So we're sampling some guys outside, so they're just rejected and ignored. And the point is that sampling uniformly over this interval here, and rejecting the ones outside corresponds to just sampling uniformly in the part that, in the acceptance region, which is here. So the lesson is that it doesn't matter too much what your rule is for expanding the interval, as long as it tries to cover this region reasonably well. You do end up with some trade-offs in that if ideally you'd like to cover as much as possible. So, for example, you could have a multimode distribution, or you could have another mode over here, maybe at this side of the distribution, and you don't know that. And if that's the case, then you want to have a very wide interval so that it's easy to jump between the two modes. But the disadvantage is that in case you don't have a mode there, you're just wasting time. It's very inefficient to be sampling these points that just end up being rejected. So this is analogous to rejection sampling somewhat. So in rejection sampling, you have some other curve that dominates our curve. Okay, here we go. So we're down here, and again we sample the horizontal line, and then we're going to define a big enough interval, which turned out to be too big, or reasonably. So we're wasting time rejecting these guys, like 3 guys already, 3 rejections in a row. 1, 2, 3. Okay, and the 4th one is accepted. And now we draw a vertical line. And we're going to uniformly sample a horizontal line somewhere. And okay, over here. And now we have a decent interval. And unfortunately, we There we go. Wasted an iteration. Now we got accepted again. And the whole point of this scheme is that your sampling points proportional to the areas of this curve. So just like in the Radford-Neal paper, this is a scheme that jumps around inside this area, and its stationary distribution is uniform inside this area, which is why, if you were to integrate out this virtual dimension, you get the desired density. The virtual dimension becomes just a density function. And you can let this run forever. I guess it's not interesting anymore. But I'm just hoping to get something down here at the bottom of the bell, just so you see how far out in the tail you can get. So this is slice sampling. The slice is these horizontal lines. Okay, so the rule that I've implemented for making the intervals is essentially you start with a very narrow interval, and you keep doubling it in both sides. So it's a symmetric interval about the initial point, and you double it in size until both ends are above the curve, and that way you know that you're sampling correctly, at least for this mode. If there's another mode, that there's no way around that. There's no guaranteed way around that. Okay, and we're back at the top of the distribution. And what happens now? We keep getting these. Where will it be? Here we go. Okay, so I might let this run for a little longer. Okay, I think that's enough.